All right, good morning. So last time we developed over the last couple of lectures, we talked about the Fourier transform and Fourier series, and we saw an application of it, for example, last time in modulation. We saw how you, for example, can understand and model, in that case, AM, the amplitude modulation, and what happens with the spectrum of that. So today we'll talk a little bit more about another application of Fourier transform, which would be quite helpful and useful for you, which is the sampling. So trying to understand sampling in the context of Fourier transform. So we apply it to the concept of sampling. So let's talk about, so we want to talk about sampling and what the implications of Fourier transform and a spectral analysis of it really is in terms of what you can or cannot do or what you should be doing when you do sampling. So before we start talking about sampling, we'll introduce a function which is an important, interesting function which is very useful for sampling, which is what we call an impulse train or a Dirac comb. So we should use it with letter, this is basically, call it SHA of sub t of lowercase t. And what it is, and you will see why we use this letter, is a sigma sum of delta of t minus nt for n from negative infinity to positive infinity. So if you look at it, if you decide to if you try to plot it, it would look like an infinite series of Dirac deltas. And these are functions of time, going in both directions, negative and positive, with the spacing of t. So this is t, this is 2t, 3t, and these are unit impulses. So they have an area of 1 each. So it's a train of impulses, equally spaced. And you can see this symbol is quite apt to present it because it shows like a couple. It's a Dirac comb, right? Or impulse train. Now, okay, so this is what it looks like, right? I mean, in time domain. What does it look like in frequency domain? If you wanted to find out what it is in frequency domain.
Why is this a cone?
Comb.
Oh, okay.
Comb.
I like
Sorry.
cone, I don't see it.
No, comb.
Cone, that makes a lot of sense.
So direct, let me just write it down. Impulse train, aka Dirac comb. All right? So what is it in frequency domain? To find out, what can we use? We can use the fact that this is periodic, right? This is a periodic waveform. So for periodic waveform, we can do actually something simpler, which we started with, which is Fourier series. So I can write a Fourier series. So I can write it in the form of, if I wanted to write it as sigma Cn e to the j omega naught t, or equivalently 2 pi f naught t, right? For n equals negative infinity to positive infinity, I should be able to do that. So what are the Cn coefficients? We knew what they were, right? Cn coefficients are 1 over t integral from negative t over 2 to t over 2 of the function, in this case, would be SHA of t, SHA sub t of t, lowercase t, e to the j 2 pi f0 t dt. Right? Now, this may look complicated, but it isn't. Because how many of these impulses will fall within this limit of integration? Only one. Which one? The one at the origin. Because the limit of integration is from here to there. Right? So it's really the integral from negative t over 2 to t over 2 of delta of t e to the j 2 pi f naught t dt, which is a lot easier to calculate, which is almost trivial. Should be trivial by now. Why? Because this function would only, this will be non-zero only at t equals 0. So the value of this thing only matters for t equals 0, which would be basically 1. So it's integral of delta over a range that includes the delta, which by definition is going to be 1. So this function, this series can also be written in this form. So it can be written as sum over n from negative infinity to positive infinity of the Cn coefficients, which are all 1, e to the j 2 pi f naught t. Right? So that sum is the impulse train, which is interesting. Yes?
Maybe G again, but what happened to the 1 over t?
Oh, well, it got missed. What happened to the 1 over t? I had an error. Thank you. I'm glad you're checking my math. All right, thanks. Now, so that's what it is, exactly, right? There's a 1 over t. What about the 1 over, yeah, the result is also 1 over t here, yes, which basically will show up here. So this is correct, but that was what missed. That one was missing. Thank you. Okay, good? We are good? No. Now, so that's an interesting thing, so that you have an infinite sum of exponentials. You could also argue that this is an infinite sum of sines and cosines. Well, more accurately, just cosines. That's producing this. So first of all, how can an infinite number of cosines produce these impulse trains? Think about it. Does that make sense? It does, right? Because think about, if you want to think about it visually, and I will do a very poor job of that, I already know that, but at least I will try. So let's say your first cosine looks like that, right? So if this is the first cosine, the fundamental. I mean, if that's an exponential one, but that's all right. Now, the second cosine would produce what? The second cosine would be at at twice the frequency. So it would go like this. Right? How about the third harmonic? The third harmonic is going to be like, so it's going to have to divide it, have the period over 1/3. So if we divide the period, if this is the period, if we divide it into 3 pieces, well, let's say this is the period. So then it's going to be and how about the fourth? It's going to be more like so on and so forth. So you will see that as you add more and more of these, they will be starting to cancel each other everywhere else because they're kind of become random eventually when you add a large number of them, right? Except for these points at the period points, exactly, at 0 and t and 2t and all those things, where all of them coincide on top of each other. So what happens is that all of them combined would produce something that goes very large here, becomes like wiggly, 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 wiggly. And then, well, in this, yeah, wiggle, 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 wiggle. And the more of these you add, the taller and narrower this becomes, and everything else goes to 0. So that's not completely unreasonable to think about this as as an infinite sum of cosines of equal height or equal magnitude. So now if you have this, which is basically the same thing as saying this, because you know these are complex conjugates, so negative and positive ones produce the cosines essentially for you. Because you have e to the j something and e to the negative j something. Yes?
Should there be an n factor in the exponent?
Yes. I'm missing an n factor here. Yeah, thank you. Otherwise, they would be all equal frequencies. Exactly. Thank you. So yeah, correct that. That's an n here. But okay, so fine. But we haven't said what it is in frequency domain yet. But it's pretty straightforward. If you want to do a Fourier transform of this, Fourier transform of this is pretty trivial, because you've already done Fourier transform of an exponential. What's the Fourier transform of an exponential with an imaginary argument? It's a delta at that frequency, right? So now for each one of them, the Fourier transform is going to be delta of f minus n f naught, for n equals negative infinity to positive infinity. So this is interesting because it says the Fourier transform of an impulse train is what? So the impulse train in time domain is what in frequency domain? Another impulse train. The only difference is that its spacing of the impulses has changed now, because f naught is really 1 over t, right? It's the spacing of these things, the period, the fundamental. So you could also write this as 1 over t sigma delta of f minus n over t for n equals negative infinity to positive infinity, which you can also show as SHA of 1 over t of f, or SHA of f naught of f. This subscript basically says what the periodicity of that function is. So the impulse train in time domain became an impulse train in frequency domain. Another impulse train in frequency domain with a couple of minor differences. Well, it's actually there's a 1 over t in front of both of them. This time I caught it before you guys did. So here basically would be an impulse train, equally spaced impulses with the areas of 1 over t, every single one of them, and then the spacing of 1 over t, or f naught. So this is 2f naught, 3f naught, etc., etc. It's kind of amazing, right? I mean, that an impulse train in time domain is also an impulse train in frequency domain. But if you think about it, it's not that surprising, because it's a periodic thing, right? It has energy at all different, only at the harmonic frequencies. And we saw that you can get it from adding equal amplitude, different frequency cosines. So they all have the same amplitudes in frequency domain. So its spectrum is like this. And you may say, okay, that's interesting, but what is it good for? Well, you can start imagining that we can use this impulse train to model sampling. When you have an analog signal, let's say, and you want to sample it, and what's the impact of that sampling on that waveform, on that signal? What happens? So let's do that. Let's do it. And I will employ your help through this process. So let's start with, let's say you have a waveform. So let's say you have an x of t that you're trying to sample. So it's a function of t. It's doing something. It's a continuous analog signal. And then I want to sample it. If I wanted to use the impulse train, what is the simplest thing you could do to just sample the values of the signal at equal times, let's say equal spacing at t, or 1 over fs, the sampling rate? What could you do to this? Multiply it by the comb, right? So if I take this and multiply it by the comb, well, let's see if I can do this properly. Okay, so let's see. So this is the comb, the impulse train. So this is Ts, T, 2T, 3T. So what's my sampling rate, by the way, in this case? 1 over t, right? How many samples per second, right? 1 over t. The sampling rate would be 1 over t. So so basically I multiply these two. What do I get? What do we get if you do that? So the product of these two is going to be, well, okay, now I have to do my best to replicate that thing. Something like that. Something like that. Right? And now these guys would be weighted by that. So what you will end up with is, I'll show it this way because they basically have different areas. Really, their heights are infinity anyway, but this way we capture the fact that they have different areas by showing them with different heights. So this is the new, let's say, y of t, the output of the signal. So the y of t is really this impulse train, which is the product of the x of t and the SHA, the sampling, or the impulse train of t times x of t. Does it make sense? So what does it look like in frequency domain? You can see that's what it is in time domain, right? So this is all time domain. Everything is time here. So what is the equivalent of this thing in frequency domain? When two things multiply in time domain, what did they do in frequency domain in Fourier in the Fourier domain? They convolve, right? So you have to calculate the convolution of the two spectra. So what was the spectrum of this thing? Well, we don't know. I mean, it's something, right? I mean, the way of the. So let's say it's a band-limited signal. So let's say x of f. Well, we symbolically show it in this form. So let's say I'm showing it with a triangle, just to show. And let's say it has a bandwidth of b, meaning that it has no energy above this bandwidth. So it's band-limited. We talked about band-limited signals, right? So let's say it's perfectly band-limited. It's a signal that you put through a perfect low-pass filter, so nothing above, it has no frequency component above b. It could be an audio signal that's band-limited at 20 kilohertz. So there's nothing about 20 kilohertz, for the sake of argument. So now I need to do what? So now, and the impulse train in frequency domain is what? It's another impulse train, right? The only thing is that the spacing is changed now. So let's say what's the spacing here is 1 over t, or fs, frequency sampling frequency. So this is f. So everything is f here. Okay? So this is an impulse train. And again, you get another one. Keeps repeating. So what do I do with these two? I convolve. Now you should be experts of convolution. That's why we practice convolution first. Because now you can apply it very easily, because now you know how to deal with these things, because you've dealt with more complex ones. So what is the convolution of these two? What happens when you convolve with an impulse? You just make a copy of it at that point. Yes?
Is B less than Fs?
Oh, that's a good question. Is B less than Fs or more than? Well, what if B was less than Fs? Okay, let's say B is less than Fs. What happens?
Then we only have one impulse that it is multiplying with wherever it is.
No, it's not multiplying. You see, it's yeah.
Or like the area is.
So this gets replicated, right, in different places. But so you're trying to avoid an overlap, right? Is that what you're trying to do? But is that the condition for no overlap? Think about it. Say again? 2b. Or Fs has to be greater than 2b, right? You may have known about this. When you sample, what's the slowest you can sample? a signal with a certain bandwidth at twice the bandwidth, right? That's called the Nyquist rate. If you haven't heard about it, now you're hearing about it. Some of you are nodding, so at least some of you have heard about it. So what does it look like? We already arrived at one of the conclusions I wanted to arrive, but that's good that you arrived at it. So if, let's say, we could get these things replicated properly, in other words, so this is at fs equals 1 over t, and this is b, negative b. It gets scaled by 1 over t, but yeah, that's a little bit beside the point at this point. But yeah, just to be complete, just make sure that we put the 1 over t here too. But now from that picture, you can easily see, if you want to avoid an overlap, if you don't want to distort the spectrum, this length has to accommodate two b's. In other words, fs, this is when fs is greater than or equal to b. Or sampling rate is greater than twice the bandwidth of the signal you're sampling. And this is called the Nyquist rate. So what happens if it's not true, if fs is not greater than 2b? Then they would start overlapping, right? So if this is not true, then you can get a messy thing. It can get messed up. The spectrum will get messed up. So for example, then you will end up with things that look like this, for this example. And you can't reconstruct it from this anymore, because that spectrum is damaged. This is called aliasing. So you can see that it's a direct conclusion from the Fourier analysis that you have this kind of behavior, the Nyquist rate of the signal. And it's a very important conclusion, in fact. By the way, if you wanted to reconstruct the signal from this impulse train, what do you need? Because this is not, clearly, this purple signal doesn't look like this. It doesn't look exactly like this. I mean, it looks similar, but it's not that. How can you reconstruct this from that? Let's say you have satisfied the Nyquist criteria, Nyquist rate. So you've sampled above the Nyquist rate. What do you need to do to recover, to generate this signal? What do you need to do? Yes?
Would that be possible with the time domain one? Because it could be just like anything in between the...
Use the frequency domain one to think about it. Use this. You're trying to reconstruct this from that. How do you take the middle one? What is the thing that will take this part out and reject the other ones? It's a low-pass filter. So you put this through the low-pass filter with the proper bandwidth. Then you can recover this if you really wanted to. Oh, what if you don't know your bandwidth? I mean, you know your sampling rate, right? You know your sampling rate. So it's basically just if you do it at half the sampling rate, then you recover it. Or if you don't recover it, it means that it was already aliased. So if it's already destroyed, that information is gone. You don't have it anyway. Or distorted, let's say. So, by the way, do you know what the sampling rate of audio on a CD is, for example? Does anyone remember? Does anyone know?
It's like 44
kilo samples, that's right. So why is it 44 kilo samples? Yeah, they want to be able to cover everything up to 20 kilohertz, and they don't want these to be just touching, right? You want to leave some margin, because in that case, if you wanted to reconstruct this, you will need a perfect brick wall filter, which we saw would be difficult to generate. You will have to wait infinite time for that last time. Now, in a CD, it's not that important, because if you have to wait 3 milliseconds extra for the music to come out from the time it was read, latency doesn't matter, right? There are certain applications where latency matters, but CD is not one. Yes?
Can you prevent aliasing by first low passing the original?
Sure, but this is assuming that it's already low pass, right? Right? But when it's low pass, it has a certain bandwidth. So if your sampling rate is less than twice that bandwidth, then aliasing will happen. You could say, okay, you know what? I cannot afford to do 44 kilobit per second, kilo samples per second. I can only do 10 kilo samples per second. So I don't want my signal to get distorted. So what do? Well, I low pass my audio to 5 kilohertz. And it's fine if I'm transmitting voice. But if I'm trying to kind of like send the music over and I want to kind of capture all the nuances and everything, then it will be lost. You could do other things. I mean, there are lots of other things you can do. I mean, this is, again, a very rather simplistic view. You could try to first compress the data, things of that sort. You could sample it at a high rate and compress it at a lower rate, depending on where the bottleneck is in your system. There are a lot of things that you can do. There are also other interesting things that you can actually do. Oversampling. A lot of, actually, again, this is like a little bit farther down the road, but many of the actual systems, they oversample. Now, it turns, because one thing that we've taken into account so far is that it's sampling, but there's another thing that we haven't taken into account here, and it's interesting, which is quantization. When you have, when you go to digital, you do two things. You do sample, right, which is this, or a variation of this. We'll see a couple of the variations of this. And you see quantization, which is basically you don't have exact levels that you had. You reduce it to a number of discrete levels, depending on how many bits you have in your A to D. So one way you can improve the quality of signals, so that introduces the so-called quantization noise. Because the deviation that quantization creates from the actual signal, you can think about it as the actual signal plus that deviation, or minus that deviation, and that would become, but that's what we call quantization noise. You can actually look at the spectrum of the quantization noise, all sorts of things. So if you wanted to minimize the quantization noise, what would you do? What's the simplest thing you need to do? You need to increase the number of bits, right? So you need a better A to D. You need going from 8-bit A to D to 12-bit A to D to 16-bit A to Ds and all those things. But now, from a practical perspective, it's actually harder to go beyond it becomes very, very difficult to go and increase the number of bits on an A to D, the resolution of the A to D. It's because of the fact that you're relying on having different elements on a chip match perfectly and all those things. And you remember, every time you add a bit, you're doubling the accuracy that you need. It's not a linear, say, oh, okay, from 8 to 12, 8 to 16, it's only a factor of 2. No, it's not a factor of 2. It's a factor of 256 improvement in accuracy and precision. So every time you add a bit, you're doubling the precision that you need. So at some point, very quickly, rapidly, you run out. And there are a lot of calibration and other kind of techniques. But it gets you to a certain level that you say it becomes diminishing in negative returns if you try to go beyond that. So what do? There is something else, and we are not going to talk about in detail. I'm just going to say it as a point of interest, is that instead of increasing the number of bits, you can actually sample at a higher rate, oversample. So instead of sampling at 44 kilobits, you sample at 250 kilosamples per second. And there's a way to trade that with the resolution of the, so you can use the sampling. In fact, one of the things that they do, a lot of these things you may even have heard, it has a 1-bit quantizer. So taking that to the limit, you can actually live with a 1-bit A to D. By the way, what's another name for a 1-bit A to D? It has a simple name. It has a name. It's called a comparator. The level, so if it's above that, it's 1. If it's below that, it's 0. Right? It's very simple to make, right? So you can actually do a 1-bit quantizer and go sample the heck out of it, just like really, really fast. And that still works. And in fact, there are some advantages to that. And there's a lot of theory and design and things of that sort around that enables you to get around a lot of other problems in the system. So that's just some point of interest. Anyway, okay, so let's talk a little bit more about this sampling business. So this is, yes, this is interesting and it's kind of like abstract enough to give us the key result. But you never sample like this, right? Because you don't have this in reality. I would conquer the world if I had this impulse. If I had one real impulse, I can conquer the universe. Because nobody would want me to use it. Right? But anyway, so we don't have something like that. What do you have? What do we have in practice? In practice, we have really a pulse train, not an impulse train. Right? So how does a pulse train look like? So let's start with our original signal, or some variation of x of t. And then let's say you want to get this, and then now instead of sampling with that impulse train, I want to sample with a pulse train. So these are a lot more well behaved. Right? So make the areas of these things 1, for example. And each one of them has a width of, let's say, Tp, pulse width. So there are 2 T's here. There's a T sampling, or Ts, or T, capital T. And then there's a T sub P, which is basically the width of the pulse. So now if I have these 2, how can I sample with these 2? Well, what do I do with these 2? I can multiply, right? I can multiply these 2. And when I multiply these 2, what do I get? What does my waveform look like? So let's say this is my original waveform. Now, when I multiply by this, I capture that waveform for that period. So those would be what would be coming out. Now, by the way, do you know what this is? It has a name for this kind of sampling. It has this kind of sampling has a name. Anyone? It's called a track and hold, because you're tracking the signal. Well, it's really track and reset in this case. It's not track and hold. Track and hold would be track and hold the value. Track and hold the value. Track and hold. That would be track and hold. This is track and reset. But anyway, so that's what it is. Now, in terms of frequency domain, what can you help me construct the spectrum of this thing? I want you guys to do it. I want you folks to try. So this, of course, has, there's nothing magical about that. So if that was x of t, I just assume that some x of f, you can assume it's like this. By the way, can you make this out of a simpler function? A triangle? Yes?
We're able to track it for short periods. Why can't we track it for a longer period?
We could. I mean, it's just a function of what the value of Tp is.
Wouldn't that just tell us what our function is?
Well, if you do it, for a special case where Tp is equal to Ts, then you basically, your output would be equal to the input. Yeah, that's true. But it's not very useful, right? I mean, it's because, and again, this is an intermediate result. So still, we'll have to do one better than this. We'll get there. But let's see what this is. But now, going back to my question, is the question is, can you think of a way of constructing this triangle out of something simpler? Using all these tricks that we've learned about convolution and all that? Can you get it out of convolution of something with itself? What is the thing that convolve with itself would give you that? A pulse. Yeah. A pulse. So a pulse with itself. So you can write it as a pulse convolved with itself. And that's useful, of course, if you wanted to know, if I ask you what's the spectrum of this thing. One way to calculate it is that you know the Fourier transform of a pulse, which is the sinc, right? So if I tell you this is the pulse convolved with itself, then what would you say the spectrum of this thing is? Sinc squared. Because they're convolved in frequency domain, so in time domain they have to be multiplying. So it's multiplied by itself, so it becomes sinc squared. So the spectrum of this thing is really sinc squared. If you start thinking about it, then it should all mesh together, right? So anyway, so let's say this is the spectrum of this thing. No, don't worry about what it is. I mean, it's just symbolic for this at this point. It could be any shape. So now, what is the spectrum of this? Now I want you to think about this. How would you tell me what the spectrum of this thing is? Yeah. A bunch of sinks that are translated. Not quite, but you are on the right track. Construct this first in time domain in your head. Tell me how you construct this out of the things that we know, out of the elementary things that we know. How do you construct this out of the impulse train, for example? If you wanted to convert this to this, what would you do to it? Convolve it with a pulse. So now you convolve those two with the pulse. What do you do in frequency domain? Multiply. So it's the spectrum of the impulse train, this spectrum multiplied by the spectrum of, or by a sinc, which is the spectrum of the pulse. Because you convolved in time domain to produce this. You can write this really as, okay, so let's do this. So you can write this as the impulse train, right, convolved with the pulse. So let me just even do my color code a little bit more. Let's go a little bit crazy with that. What colors have I used? Okay, so let's say you can write this as the impulse train convolved with the pulse. Therefore, in frequency domain, it would be what? It would be the alternative impulse train, 1 over t's, times the spectrum of that, which is a sinc. Now, if that's a narrow pulse, what do you expect the sinc to be, wide or narrow? Wide, right? Wide in one domain, narrow in the other domain. So that would be a wide sinc. And this is 1 over Tp for F. Right? So what's this, the red spectrum, which is the resultant of these two? So that red spectrum is similar to the original impulse train spectrum, just weighted. So the impulses that are farther away gets weighted. So the middle impulses are bigger, they become smaller and smaller, and some of them become negative and all those things farther down. So what do I need to do to these two to produce my purple signal? What happened in time domain to these, the red and blue? So here I should do what? Convolve. And when I convolve these, what do I get? So what's my purple spectrum? What is it? Yeah, it would be just similar to that, except for the fact that since this gets convolved with smaller impulses down the road, the triangles become a little bit smaller as you go down. Their heights get adjusted. But the shape of the individual triangles is not messed up, right? Because it's the triangle that gets convolved with an impulse. That's already weighted. Okay? We're good with this? So is anything changed as far as Nyquist criterion is concerned? If you wanted to reconstruct your signal perfectly, you still have to have the same criterion, right? Because this is your B, this is your Fs, it's 1 over Ts, and then this is the bandwidth of the signal. Okay, but now in practice, you don't actually even do this. Most of the time, you actually do sample and hold. You may have heard sample and hold, right? You make a sample and hold it. Basically, you take a sample and you keep that value, and that's when your A to D starts working on it and starts converting it. So you don't want your input to the A to D to be constantly changing as it's working, because it can actually throw it off, and it can actually, depending on how the A to D work, it can result in significant errors. Just to tell you how this kind of errors can happen. Let's say you have a 4-bit A to D. Let's say you are initially at the value, at the point that it would correspond to point 0, 1, 1, 1, right? And then it starts sampling, so it determines that the first bit is 0. So it tries to go and determine the subsequent bits. In the meantime, the input has changed a little bit higher, so it has gone to the point where it's 1, 0, 0, 0. That says, oh, the next bit is 0, the next bit is 0, the next bit is 0. So it gets 0, 0, 0, 0, 0 for something that should have been either 0, 1, 1, 1 or 1, 0, 0, 0, 0. 1, 0, 0, 0. Right? So you want to hold the value while the A to D works. For most practical A to D, there are different kinds. There's some of them that naturally sample with it. I mean, there are many different architectures for A to Ds and things of that sort. Again, which is not subject of this class. So, but anyway, so if you wanted to go down that route, what would change here? Let's do it here. Well, let's do a new one. So help me reconstruct, or construct, I guess, that. So essentially, I want to be able to, so if this is my original signal in time domain, x of t, I want to be able to produce this. I want to be able to produce a waveform. So let's say if I can reproduce that to some extent. I want something that looks like this. Or it could be in the middle. Let's say something that happens in the middle. It makes your life a little bit easier. So let's say it samples the midpoint. So how can I construct this? Again, this is an exercise in construction of things, right? Can you think of a way of constructing this? Can anyone think of a way of constructing this? You want to try it? You seem to be nodding. Alex?
Oh, no, I was looking down to raise. No idea.
Daniel, do you want to try? Anyone else? Oh, Garrett.
Can you do it in 2 steps?
Okay, 2 steps is fine.
Multiply by the Dirac cone and then convolve from the pole.
Right, yeah. So first multiply by Dirac to get this, right? Now can you construct that from this? Now it should be easier, right? So how do you construct this from that? How do you construct it? Convolve it with the pulse. So the order of events has a little bit changed, right? So you take the x of t, and then you multiply it by the Dirac the pulse train. And then you take this, so this is my gigantic parenthesis, vertical parentheses, and convolve it with the pulse. This is my upside, sideways equals. Oh, I can make this equals. Does it make sense? So if you take this and multiply by it and then convolve by this, you get that. If you wanted to have it sideways like I just had it, to sample the beginning of the signal, not in the middle of it, what would you do? You just convolve it with the pulse that's sideways, the pulse that's here. Then it puts it there. Right? You can see I can actually construct a lot of interesting things with these two operations. So what is the spectrum of this thing now? So let's look at the spectrum. So let's assume that the original spectrum looks like this again. And then now the spectrum of the impulse train, of course, we know it's another impulse train. So this is going to be an impulse train. Let's say it's sampling fast enough, so these are far apart. Ts, Fs, negative Fs, 1 over t, which doesn't really matter in this discussion, but anyway. Now, when I multiply, so what do I need to do with these two? What did I do here between these two? Multiplied. So what do I do here? Convolve, right? So these two get convolved. So what do they produce? This basically gets replicated here and there and there. So this is basically what we did here. Right? So this is what we've done so far, is exactly this. Now, what do I need to do? So I have to close my parentheses around this thing. And now I took this result, right, which is the convolution of these two, and do what with this result? What did I do here? Convolve. So what do I do here? Multiply. By what? The spectrum of that sink. So if it's a narrow pulse, the sink should be wide. So I multiply this by that. And what do I get? So what does that look like? Think about it. What does that look like? Just multiply this function by that function, right? What happens to it? No, I didn't already do that. What I did already was the opposite kind of. So I convolve with this. I convolve with the convolution of these two. So that the order of parentheses is different. There, the parentheses were here. So I've had first convolve these two and then convolve with that. Here, I am, which one was it? Okay, yeah. Here, I'm convolving these two first, then multiplying by this. So here, okay, wait a second. I think there was a mistake here. This should be, yeah, this convolution becomes a product. So there was a product here inside, and then convolve with that. Here, there's a convolution inside, then the product is outside the parentheses. And they produce different waveforms. This is different from this. Okay? So what does it look like? Now this one does something to it, right? This actually distorts the shape of that triangle because you're multiplying it by some function. So it makes it a little bit, depending on how narrow or wide that thing is, that sink is. So and then the other one here is that basically you start off with something like that, and then you go down. And then you go like this. Right? It gets a little bit distorted. So this operation causes distortion to the signal. Now, is this completely hopeless? Not really, if you know it, because the distortion is deterministic. Right? If you have deterministic distortion, you're usually not hopeless. Because you can always, and if it doesn't change and if it's deterministic, right? If you know ahead of time exactly, because you can predict exactly what it's going to be, because it's a function of the sink and the shape and all those things, you can just apply the inverse function to the digital data when you deal with that. So you can take the 1 over sink over this range and multiply whatever comes out by that in frequency domain. I mean, it's a little bit easier said than done, but it's actually doable. Okay? So that's a very simple view of sampling, right? Now, Fourier transform is basically has many applications, many different. I mean, it appears almost everywhere, right? Let me just show you, kind of like throw you something very simple, and we'll take it just to show you another way of thinking about it, because everything we've done so far is in time domain. But now let's see if we can. It was time and frequency, right? But it doesn't even have to be temporal. It can be spatial. You can do Fourier transform in space. Actually, that was the reason the Fourier series and Fourier transform were developed initially for heat transfer. And it's in space. And a lot of electromagnetic problems, for example, are solved with Fourier transform in space, in x, y, and z, for example, you can apply. So let me show you something kind of cute. So let's say you have a waveform. Let's say an optical waveform. Let's say it's light. Let's say you have a plane wave coming towards you, right? It's an optical wave. Light coming to you from a very distant source. Let's say from a distant star, or from the sun would be a reasonable approximation, although you can still see the diameter of that. Not that you want to look at it directly. But anyway, so it's coming in, and let's say you have an idealized lens. So an ideal optical lens in the sense that it is really large enough and it doesn't have any spherical aberration. What does this lens do? So this is, let's say, it's a convex lens, right? So now let's say, so what does it do? Let's say this is the focal length, f. This f has nothing to do with the other f. So what happens? What does it do if you have a plane wave coming in and at focal length, if you're cruel, you burn ants. Yeah, or paper, if you're less cruel. So what happens is that you have this, from a geometric optics perspective, you have these things, you have a concentration here, right? So let's think about this direction. I mean, it should be really y, but I call it x. So what I had was something that was completely flat, infinitely wide, right? The waveform, the energy of the signal was uniformly distributed, right? So in x, what I had is, this is the signal, right? Here, at this plane. Now, at this point, what do I have? All of that energy, we can call it F, is where? If this is also like whatever, F. Here, right? Does it remind you of something? Now, if I put an aperture here, this is really, you really need to do a two-dimensional Fourier transform, which is very commonly used in a lot of this thing, in computer vision, a lot of different places. But let's say I put an aperture, meaning that I block the signal over a range. So I create an opening here. Let's make it symmetrical. Right? Now, if I create an opening here, do you agree that the signal at that point, beyond this point, on this plane, looks like that? What do you expect to see on what do you see on the other side? Don't you see the sink? This has a name, right? In optics. What is it called? Diffraction. It's the same thing. It is diffraction. So in fact, a lens here and this transfer in space corresponds to a Fourier transform, a 2D Fourier transform. And there's a whole field around this. It's called Fourier optics. There are people who make and have made their livings off of this business. If you try to even actually design optical instruments, precision optical instruments, you do have much more sophisticated things with this and use a Fourier transform extensively for doing that. You can think about actually even modifying the shape of your aperture or controlling, if you could put that, for example, an LCD here or something like that to change you can even control the change of phase and amplitude and create different things here, right? So now, what happens if I make my aperture very, very small? So if I make it very small, make my aperture very narrow, then this thing becomes very, very wide. That tells you about how small a point you can, because ideally if you're doing imaging, for example, if you're making a camera, right? What does this planar waveform correspond to? It's a point source at a very large distance, right? So you want to map it to the impulse. But now if you start closing your aperture, then what happens is that you can't even form an image that's very precise. The opening of the lens, right? So there will be a limit. So in essence, if you have 2 points that are very close to each other, 2 stars that you're trying to resolve, for example, at a very large distance, if you don't have a sufficiently large aperture, what happens is that they will correspond to 2 sinks that are a little bit off with each other, but they will overlap, and then you won't be able to see them. So that tells you, that's actually how you determine the resolution of a telescope or a camera. You've seen the good cameras have big wide lenses, kind of gigantic, even that one has a reasonably big one on it, right? And the ones on your phone, they're nice and they do a lot of signal processing to capture, but there's no way this can capture the same image quality as that. And there's no way that can capture the same image quality as a telescope, like a 200-inch telescope, or like 100, or 10-meter telescope, right? So that's why you make a larger and larger telescope, because you want to kind of get finer and finer resolution. And it all comes down really to Fourier transform. There's an easy way to see that. All right. Any questions? No? All right. Let's take a quick break.